Hello and welcome to a new episode of Today You Learned. So the topic I wanted to show to you today is I have called advanced sniffing. So sniffing, you might know from somewhere else, is actually where we interact with the network often. So often when thinking about sniffing, we're talking about poisoning, R poisoning, DHCP poisoning or something else. And that's of course kind of tedious and hard to do. Advanced sniffing, if you know how to use it and you know what it means, is actually more or less easier, right? So what I mean with advanced sniffing is actually very clear from the next picture, namely the obligatory Wireshark screenshot. No sniffing introduction is complete without Wireshark, right? So this is an example of a PCAP file, and will be the entire series about. Advanced sniffing has something to do with these three protocols that we see right here. We have MDNS, or multicast DNS, LLMNR, and then NBNS, NetBIOS. So each of these protocols, they have several things in common. They have their own, some are older, some are more recent. So Windows systems before Vista tend to use more NetBIOS environments. Windows systems beyond Vista tend to use more LLMNR and MDNS, things like that. But they share several similarities, mostly that they are a replacement or a predecessor for something called DNS. DNS is how do I find an IP address, IPv4, IPv6, that corresponds with a host name. So for example, we have a host name right here. This is actually an example of a NetBIOS name. NetBIOS name typically does not have dots in it, is not a fully qualified domain name, it's just a unique name, which is often similar to the host name, so we can see this right here. Another example for MDNS, which means multicast DNS, we see here, is actually very similar to regular domain name systems. It even runs on a similar port. Regular DNS is port 53. This one runs on port UDP 5353, so 5353. And as you can see, it even uses the same terminology. An A record would be for IPv4 addresses, quadruple A is for IPv6, and so on. It asks questions and others respond to it. And LLMNR is used for specific applications that can use this to find information via directed queries. Well, I say directed, that's not really the case, and this is actually the entire input of our advanced sniffing portion of here, namely that not a single session that you see here with a source and a destination is actually a communication between a single device and a single other device. If you look very closely, you can see that this destination right here is actually something called a broadcast IP address. So this is not a usable IP address in the given subnet, it's a /24, the subnet mask. So this means that these packets are actually being delivered to every single device on the network. The same goes for this MDNS packet. This is not a regular IP address, but it's something called a multicast IP address. It's not a usable address either. If something is sending data to this address, it's being delivered to every single device on the network. So even the hackers that might be connected, your smartphone that is connected to the network, actually gets every single packet that you see in this capture. Another one is right here. This is also a multicast address, but then for IPv6. We have another one right here for LMNR, which is also a multicast address. So each of these is being transmitted over to the network, and they mean the same. They all say, please help me, I am looking for this IP address, this MAC address, this application communication, and so on and so forth. And that's what we will abuse. So just very quickly, I will show a couple of slides. So for those who are interested in how to prevent this kind of data showing up on your network, this is some more details on LLMNR, and also not uninteresting, it's actually the default. Each of these applications or protocols is default present on any Windows system from the last 10 years, and up until and including Windows 11, the newest one. The demonstration will be on that one. So here we have some information about LLMNR, which is enabled via this, checkbox. For NetBIOS, we can see some information right here, but this is then where you can disable it. So by default, the LM hosts lookup, this is a different name. It's NetBIOS lookup, but Windows has called it WINS. So this is a way of disabling NetBIOS if you were to disable it if you want to disable it. So this is some information on that one. And then MDNS is actually one that is being used by more applications rather than operating systems entirely, and even further than Windows. These are actually icons that correspond with Avahi, which is a Linux implementation, and Bonjour, which is known from Apple, but it has different implementations as well, to discover devices on the network. One example would be Raspberry Pi.local. If you have ever connected to Raspberry Pi on the network via Raspberry Pi.local, or a NAS via Synology.local, or a Netgear via Netgear.local, or whatever, it uses either MDNS or LLMNR or both. It depends a little bit which one gets the first response, which one has the first IP address for the application to use. So now that we know this, how can we abuse this knowledge, right? That's all what hacking is, knowing how something works and then abusing it. So we know about these new types of protocols that are all over the place. Even if we just launch a Wireshark and do nothing, we can see, given some time and given some activity on the network, we will see these applications, these protocols pass by. So if you want to visualize them and if you want to force them to happen more closely, there's actually a tool built in Windows called RPC Ping, which simulates a Windows application connecting and authenticating with the local user to a certain device. If the device does not exist, and it is not in the host file or not in the LM host file and so on, it will actually connect or try to connect to or send out these kind of packets to try to find IP addresses to connect to. Or even if we just press the start button and enter something like this, which I will demonstrate, well, this I will demonstrate in the second video, this will be demonstrated in a couple of seconds or minutes. So if these kinds of protocols are all around, what if we try to first sniff those multicast broadcast addresses and then respond to them as if we were the legitimate party to communicate, right? So if we are a hacker, we see these communications, why not respond, be gentle, and just tell the victim, if you want to communicate with blah blah, or does not exist, or does exist but is not in the host file, please communicate with me. So there's a tool for that. It's called Responder and it's built into Kali, and it is actually nothing else than a responder for these protocols. Actually, all four of them. So DNS is here not by accident. It also responds if there were some DNS requests directed to Kali or to the machine running Responder, it would also respond to them. So how does that work? So by default, without any extra options, by default, Responder will respond positively, of course, to any of these protocols that are passing by or that are seen by our operating system or hacking operating system. Of course, once you have respond, or once Responder has response, please, I do want to talk to you, then the operating system will switch over to a more known application to actually perform the authentication. And that application listener has to be built into our responder. In this case, these are the default application listeners, so protocols that our responder is able to capture data, authentication credentials or authentication data, and it will be stored, all of these results and communication will be stored in user share responder logs, which is the default location on Kali. It can of course be different if you install Responder on another operating system, which is perfectly possible, of course. It's a Python tool, if I'm not mistaken. So let's demonstrate that. Let's first show you what I have prepared. So we have our hacking machine right here. It's a general normal Kali environment. I don't think I have installed anything special right here. It's Responder is default. And then here on the left side, we have our victim. So the victim network, so they are all in the same network, exists actually from 3 different machines. We have a primary or a first domain controller. Then we have a second domain controller, just to have some toys to play with. And then we have a fully up to date up until the date that you can see right here, Windows 11. The same goes, by the way, for the Windows Server 2022s right here. They are fully updated, antivirus is enabled, all the settings are default, the firewall is configured. The only thing I have changed in the firewall is enabled SMB on Windows 11. That's not the default anymore if you join it to a domain. And why did I do that? To be able to show you the very first demonstration, because maybe we want to know how the network looks like, right? To find which hosts are actually on the network. Well, you can use Nmap for that, of course. You can even use CrackMap. But Responder has a built-in discovery tool, scanning tool. This is, of course, an active scanning tool. It's called Run Finger, and what I have to do to use it is just to specify the IP address I want to scan. So let me switch over to the other tab to show you the network that you're in. So this is the network 50.whatever/24. So this is the network that I will scan, and it takes not too long, and it should be very quickly find out these three machines, right? So it even specifies a lot of details. For example, the domain, which we can actually also see here, of course. This is the domain name, demo22. You can see that we have a 75, a 76 and a 90. 75 and 76 based on the build codes and the fact that they have signing enabled, which I will come back to later, means that it's probably a server 2019 or newer, and since this is the build code, it will be newer, so server 2022. And then another one, so he reads out SMB2. Another one has an even newer build code, which corresponds to Windows 11, right? And it has signing false, which is the default on Windows clients, all Windows clients, by the way. And they also have SMB version 1 disabled, which means that they are fairly recent. The same response will be gotten if we try the same, but then with CrackMap exec. So like this. So he does the same, uses SMB because that's what I specified, and the biggest difference is the fact that he also is able to read out the host name, which is not possible right here. And he sees that we have a DCO1, a DCO2, and then a Windows 11 from probably user David, right? Okay, nothing fancy. Let's dive into Responder itself. Maybe I will switch over here. So Responder is very simple to use. If you don't specify anything, he actually tells you what to do. So we have to specify our adapter and maybe make it verbose so that we see some more information. So the default of Responder is to poison these four protocols. Even DHCP is possible, but that's disabled by default. Actually, I just noticed something else that is not default, which is for a different demo. So let me first clean that up for you, otherwise my demo will actually fail. So by default, all these listeners are on, and I just noticed that they weren't in the demo I just showed you. So these are the servers or application listeners. So besides these two, everything is now on, which is what I want. I want to be able to speak the protocol, capture any credentials or authentication data coming from these applications. Then you have some advanced options, which we will come back to. This is not unimportant, so we have our own IP address, the NIC of course, and then for this I will come back to that. But here we have a fully generated random every time I run Responder, so the previous time it would be something else right here. This is actually randomized, so just to, if we respond and we have to interact disclosing our own host name, this is the host name that we will be using, and this would be the domain that we will be using during the disclosure. DCE RPC, for example, uses something called an ephemeral port, right? Which is a random port. That's a different name and a difficult name apparently to just tell that this is a random port above 40,000 or 45,000 dynamic port, and this is the one that he has chosen. Just if you wanted to take a look at this in Wireshark or whatever, then we can filter on that. Not important. As you can see, he is listening for events. These are just out-of-the-box systems, so by default they don't really do much active stuff. If I were to reboot this system, we would already see something, but maybe let's start off pretty simple and let's fake something, right? Let's say that we want to connect using FTP with username. My name, for example, was here at, and then some name that does not exist, right? Just to show you something. So does not exist. What does Windows do? Windows first tries normal DNS, but there's no response to that. I don't think it even starts with normal DNS. I think DNS is corresponded with these protocols that we see right here. Well, the first thing he really does is look into the host file and the LM host file, which contain nothing by default, so no problem right there. And then he tries to find the IP address for does not exist. It's being sent to the entire network. Responder sees that, says, I am here, I want to respond to that. you can connect to me, and then here we actually see the client IP address. In this case, it has used both IPv4 and IPv6, but IPv6 was faster and preferred. More on that later as well. And we have a clear text username and password. If you have FTP servers that communicate every hour or something, then chances are very large, if the DNS is expired or something like that, that these will also pop up right here. Okay, so that's one example. A second example, and let's make it a little bit more difficult, is to use, for example, that RPC ping command like this. So what we can do is we can connect with a socket of whatever host name that we prefer, and then we specify that we want to connect using the built-in NTLM authentication. This command actually simulates something else that we can do that happens more or less on a daily basis, and I will demonstrate that in the next video. The next video will be, every new video is cooler than the previous, of course. So this will be simulated. I'm pressing enter right now. So he performs that RPC ping command. You can see that it also again generated several MDNS and LMNR commands, and then we have poisoned that, or responder has poisoned that. Poisoned meaning answered, responded to that. And what we have now is, of course, the same client. A username, because that is actually the username of the user that is currently logged in. Apparently it's a domain user. And then here we have his NTLM v2 SSP hash. More details on that type of hash in the next video, but in short, this type of hash is actually not replayable. We cannot perform something called the pass the hash with this hash. It's based on challenges and salts. You can actually see the salt. I believe this is the salt right here, and then this is the challenge right here, the challenge, and then the response, the numbers used once, are actually in here together with some other data. As you can see, there are some Unicode characters in there because it's SSP. SSP is a little bit longer, has timestamps and other stuff. Not important right now. What can we do with this? The only real thing that we can do with this hash right now is to try to crack it. So let me show you where that hash is actually stored. It's in the slides as well. It's in user share responder loss. If we take a look, we have our full loss, and then we have the clear text credentials that we saw before right here. And then this is probably that hash. So we can actually verify that, of course. Yes, we have our hash. So we can try to crack that. Crack that, for example, with something called hashcat. It's actually very simple. I have to specify the location of the hash or the file of the hash. And then let's perform something called a dictionary attack. So word list nmap, a dictionary attack. So he will now try to crack the passwords, trying out every single password that is in this word list. He automatically, that's something new in Hashcat, he automatically detects what kind of hash it is, and in this case he has found that it is a hash of type net NTLM v2. And then since there's only one auto-detected right now, he will go with that, and I believe he is now preparing the hardware, preparing the memory to have that digest, as he called it, and the hash loaded into memory, and then starts to actually perform the crack. 5,000 passwords is very short. He actually does it in 0 seconds. Here we see our hash, and this is the clear text password for user David of domain demo22. Can we verify that? Of course we can. Let's take a look if we can, for example, on DC01. Yes, that works. Let's try it out for David, password 123, and a plus means that this is indeed a functional credential. Deliberately, David is not a domain admin, is not a local admin on this system, is a normal domain user and has no specific credentials. Nevertheless, we actually do have his clear text credentials. More demos in the next video, of course. Thank you. And as always, keep learning.